Hey again, guys. So before we talked about arithmetic sequences, so that's when you are increasing or decreasing by the same constant rate, adding or subtracting. So now we're going to look at a different kind of sequence. So if we look at this sequence, 3, 6, 12, 24, what pattern do you notice? Well, it's not adding or subtracting a constant number. It's actually multiplying. So 3 times 2, 6 times 2, 12 times 2. So we're multiplying by 2 each time. And this is not called a geometric sequence. It's actually called, or sorry, not called an arithmetic sequence. It's called a geometric sequence. And it's when each term of the sequence is the multiple of a previous term and some number we're going to call r. So in this case, the multiple of the previous term would be like 6 is a multiple of 3 and 2. 12 is a multiple of 6 and 2, and so on. So that is the difference between arithmetic and geometric. Arithmetic is when you're adding and subtracting by the same number each time, and then geometric is when you're multiplying, and then we'll get to dividing by the same number each time. So just like with arithmetic, we do have two different formulas. We have the recursive formula, which is any number is the previous number times r, which we'll call the common ratio. That should sound familiar from when we were talking about exponential functions. So remember before for arithmetic, this is plus or minus a d value. This one is multiplied by r. But again, the more useful one is our explicit formula. So we take the first term and we times it by that common ratio to the n minus 1 power. So this has a lot to do with exponential functions, and I'll show you that in a moment. So these are the two formulas that we're going to use for geometric sequences. So here's a sequence, -2, 4, -8, 16, so on. So if we're talking about the recursive formula, we are taking the previous term, and what are we multiplying by? So, well, what do we multiply -2 by to get -4? That would be -2. 4 times -2 would also give us -8. -8 times -2 would also give us 16. So we're multiplying this by -2 each time. So if we're looking for the explicit formula, remember we're taking the first term. So in this case is -2. In the parentheses would be our common ratio. So what is our common multiplication each time? That's also -2. That just happens to be a coincidence for this problem. And we're going to raise that to the n minus 1 power. And again, remember that n minus 1 is talking about the previous term. And that's an exponent, just like we did with exponential functions. So just like with arithmetic, we want to find certain terms in our sequence. So if we were asked to find the 12th term, that would be a sub 12. It would be -2 times -2 to the 12 minus 1 power. Okay, so let's go ahead and get out our calculator for this. So we have a sub 12 equals -2 times -2, 12 minus 1 would be to the 11th power. So we want to type in -2, and on calculators on your phone, you may see this button right here. So that's raising it to, we want to raise it to the 11th power. And then we also want to multiply it by that -2, which is our first term. So this would actually be 496 would be our 12th term. And so that gets rather large fast, just like exponential functions increase at a faster rate than linear functions. Okay, so the first 4 terms of a geometric sequence are 7, 14, 28, 56. So what is happening each time? So if we write our recursive formula, we're going to take the previous term, and what are we multiplying by? Well, to get from 7 to 14 would be 2, and then to 28 would be 2, and then 56 would be times 2. So we always take that previous term and multiply it by 2. Remember the explicit formula, we take the first term, which is 7, and we're going to multiply it by our common ratio, which is 2, and we're raising that to the n minus 1 power. And this would like us to find the 20th term of the sequence. So 7 times 2, 20 minus 1 would be to the 19th power here. So let's clear this out. So we want to take 2, we're raising that to the 19th power, and then we're multiplying that all by 7. So that's 3,670,016. And that would be the 20th term of the sequence. So just like arithmetic sequences made a linear graph. So let's look and see what this sequence makes on a graph. And you can see that it makes an exponential. And that's because we're multiplying by some number each time. So our first term was 7, our second term was 14, our third term was 28, and our fourth term was 56. And you can see over here that I typed in that formula exactly as I found the explicit formula. And except I used an X instead of an N, but that's okay. All right, so let's look at another problem. So an art gallery was showcasing a 6-inch long photo of a geometric landscape. The picture was enlarged 10 times, each by 125%. Enter the formulas that would give the length of the enlarged print. So if we're talking about the first term, the original term would be 6 because that would be our original photo, or A sub 1. So our recursive formula would be the previous term. And what are we multiplying by each time? Well, we're not multiplying by 125 because that's a percent. We want to change that percent to a decimal. So we're actually going to multiply it by 1.25 each time. And then our explicit formula is we want to take the first term, which is 6, and we want to multiply that by 0.125 and raise it to the n minus 1 power. So if we are actually enlarging this 10 times, let's do A sub 10. So 6 times 1.25, 10 minus 1 would be to the 9th power. So let's try that, 1.25 to the 9th power times 6. That now would be about 45 inches long for that new geometric landscape, which is almost 4 feet. So if we were enlarging that 10 times, it would be about 4 feet long. All right, so we want to go ahead and just sketch this graph from this sequence. So what's happening each time? It is going to be multiplied by 2. So I'm going to go ahead and say that my x-axis is going to go up by 1s, and we'll say my y-axis is going to go up by 5. So my first term is 3, which would be about right there. Second term is 6, which would be about there. Third term is 12. Fourth term is 5, 10, 15, 20, about there. Fifth term, 5, 10, 15, 20, 25, 30, 35, 40, 45, there. And then my sixth term, 50, 55, 60, 65, 70, 75, 80, 85, 90, 96. And you can see, and again, I'll try my best to sketch this. I'm not very good, but it does end up following that exponential pattern when we are multiplying by that same number each time. Remember, when you were adding and subtracting, it followed that. All right, guys, make sure to let me know if you have any questions or concerns about any of these problems, and I look forward to hearing from you. Bye.